went through a detailed understanding of Newton's laws of motion and the basis or the foundation that they form in starting the aerospace propulsion concepts and designs. Every engine starts from Newton's laws of motion as a fundamental concept of design, and that's what we reviewed in the last lecture. In today's lecture, we are now going to move ahead and actually start looking at an aircraft as a whole and understand first of all why and where is propulsion required. This question may seem funny to you because you are already studying for a GATE exam and you would say propulsion is a subject given as a part of my curriculum. So maybe that is why propulsion is required? No. The fundamental reason why the aerospace propulsion as a branch has started out and carved out separately as a full discipline has its origin or roots in the history of aviation. Let's quickly take a look at it in a 1 minute. When the Wright brothers in their historic flight actually flew the aircraft, or before that the several attempts by the mankind to fly in the air had started, first and foremost form of design always would be a glider. Some people used compressed air as a motivation, but the gliding on its own as a concept is a passive form of aviation, which means the energy stored in an object either as a gravitational potential, the energy because of the height that you may have in the glider, or in a compressed air as a form of a balloon or a compressed air system energy is given. Once that energy is there, aircraft comes down slowly as a glider. So if this is my aircraft, then the aircraft has a certain amount of energy, and the moment it starts descending, it loses that energy slowly, which means it is a passive form of driving aircraft forward. You're entirely relying on aerodynamics and structures to leverage the most and at maximum efficiency the energy already stored. But this is not convenient if I want to fly transatlantic or if I actually want to fly from point A to point B in a robust manner. So the roots of propulsion are in this fundamental question. How do you propel an aircraft in its motion so that it can perform all the motion and maneuvers starting from takeoff to climb, to cruise, to loiter, to glide, to come down, to touch down, to descend, all of this. And in military, of course, other 100 complex maneuvers. Therefore, the propulsion as a concept is pretty critical to ensure that aircraft can perform these maneuvers, which means it is an active form of imparting energy to a flying object. That's the first and foremost answer to this question. Having found this basic foundation of the aircraft propulsion in its history as we understood now, let's quickly now look one by one of this aspect of the question of why and where is aircraft propulsion required. So this is where we start. In the previous lecture, you are now getting familiarized with this format of interactive video and parallel tutoring using the PPT or a whiteboard problem solving. We will extensively use this over for this entire lecture series. So in the previous lecture, after Newton's law, in today's lecture, as you read the title, it is where is propulsion required and why. You see, critically, the propulsion is not only in aviation I have mentioned. It is of course required in rockets. And in rocket propulsion, the fundamental gamut is itself different because you don't want to just make anything object fly, but you actually want to lift it up high in the orbit. So that's why the propulsion as a word is a broader concept. Fundamentally, in the GATE, we will have aircraft as a propulsion concept more widely covered. But of course, in the later part of the lecture series, rocket propulsion will also be covered. But the roots or the genesis of propulsion remain the same that we discussed. So if you recap, we have just completed and tick marked our previous lecture. This is about a 20-minute lecture again, where we will look fundamentally on propulsion requirements. If we again go back to this exciting diagram that we looked at in the previous lecture, the A portion of this, where the engine is shown from a front view, and in B portion it has been zoomed in. You see a lot of these component systems, the propeller, the intake, there is the combustion chamber, there is a turbine, then there is a nozzle at the exit. The whole function of this entire block is to derive an energy and impart that energy to the aircraft. Where does energy come from? The fuel that is stored. It is exactly like a car. In the automobile, you have a fuel which is undergoing into a reciprocating engine or undergoing through the piston engine, in which the fuel is added, the air is compressed, the air fuel mixture heated up, makes the piston lift up, and the motion of the piston is used to drive a cam and therefore the wheels and hence the motion. Which means fundamentally the automotive industry relies on extracting fuel energy to directly impart the motion, and the friction on the ground is the source of motion transfer. And this concept is very much pivotal in the nature. Why? On the ground you have a solid car resting on the surface, and when the fuel energy is imparted, the wheel that rotates about a point, it is a pure rotational motion about a point. The friction causes the transfer of motion and hence the linear motion. In air you don't have this choice, which means the fundamental thermodynamic cycles, as we will see, is different in aircraft as compared to ground automotive air engine. The automotive engine derives the fuel power, propels the automotive forward using the friction as a force transfer or a motion transfer mechanism. Even minutely, if you look, the piston which is moving up and down transfers that energy. Whereas in aircraft, it is these rotatory compressor, piston compressor or a turbine components and then the nozzle which create this energy. Which means the transfer of motion is in one axis and it is the same axis is in which the object is also moving. Slightly mechanical difference, but very, very subtle and very, very critical to remember at this point of time. So in aircraft, again, if we go back, we see this entire engine which is giving the power to the object which is aircraft using fuel as an energy source. Now, let's revisit our standard cruise mode equation, where we said that in a cruise mode, this aircraft is subjected to a lift which is exactly equal to weight. That's why it maintains its altitude, it maintains its constant altitude profile. There is no external force in this direction. The forward thrust is exactly same as the drag experienced by this object because of its aerodynamic shape passing through air as a fluid. Because every object, as we know from our fluid mechanics, when in motion in a fluid, will experience certain friction, which is nothing but drag. Now, this JSW is flying in constant JSF. This JSF aircraft is flying in constant speed. Because there is no acceleration, you don't require any additional thrust, so that the T delta, that is the additional thrust, is equal to MA. No additional is required. Only you have to match the drag. Sum of all forces is 0. We saw this. Entire weight of aircraft is perfectly balanced by the lift. Again, a simplified assumption, lift actually will not be vertical like this, but will have a component like this. A component in slightly this direction, which will have some resolution. But that is fine. So once we have understood this basic concept in the previous lecture, now let us look at this important graph. This graph is about L by D for various velocities versus the thrust. Very important concept. When we start plotting our thrust with velocity, you experience actually a parabolic curve, a semi-parabolic curve, which means this is almost like an economic competition curve that in economics people use always often. Question we have to ask ourselves is why? And the answer is very simple. Initially, at extremely low velocities, the thrust is very much different, because when the airplane is at a given altitude, first let's imagine it is at a sea level, the thrust will be very much lower as compared to your thrust that you would require, simply because there is no enough momentum or the work to be extracted. That is also the reason why on the ground initially at the start you have to insert a lot of fuel to burn so that the turbine starts, and that's why you have these auxiliary power plants. As the velocity increases, the forced thrust actually keeps reducing, which means there is a tendency where the high thrust actually starts coming down. This is the case because at these particular cases, the drag and the lift are not yet balanced. So you remember this equations. Now when you are having this not in cruise mode but in a different increasing velocity maneuvers, the drag performs as a square function of velocity, and so does the lift. But at one point when L by D, which is the design parameter, is optimized, you reach a point where because of the lift, majority of the weight is being taken care and drag is minimum. That's where the thrust produced is actually good, but the required thrust is minimum. Never ever get confused within the axis of these. It is TR, which is thrust required curve. It is not TD, which means the thrust that you have been asking for from this aircraft engine is now going down as the velocity increases. At zero velocity, of course, you would say it needs maximum, as we discussed, because you have to first start the engine, you have to take off. Moment you reach a point where L by D is optimized, this is the best gliding curve also, if you remember. So therefore, as L by D, which is the gliding portion, the best optimum gliding trajectory that happens is reached, that means aerodynamically you have extracted your performance to an optimum, required thrust is at its minimum. What happens then? As velocity increases, even though lift is increasing, you don't need that much lift because your weight is not so much required to be balanced. So the excess lift actually causes it to go into a circular path, or to ensure that it now doesn't go into circular path, you have to adjust using your flaps and using your ailerons, and therefore that additional lift because of these high velocities is not very optimally useful. But drag is always a penalizing drag. No matter what you do with lift, it says, boss, my job is to penalize you. With additional velocities, which is in this regimes, the regimes of higher velocities, drag increases. Hence, to match it, the thrust required keeps increasing. What is the CP1 at sea level? It is simply the point to make that at a sea level point, this is the curve that is plotted. As you increase the altitude, the curve shifts, moving up and down depending on the requirements and depending on the sizing. Now, what is therefore the aspect? We see that minimum TR is when aircraft is flying at L by D max. So select a flight speed V infinity. What is CL? It is the coefficient of lift, which is weight upon half rho V square S. S is the weighted surface area. It is not just area of a wing. We know from our aerodynamics. You again calculate CD, which is the parabolic drag equation. You calculate CL by CD and hence the thrust required. If you optimize, the thrust required at any velocity is W upon CL by CD. Hence, aerodynamic plays equally important role in the requirement of the thrust, and it also tells you that no matter what I do, I need minimum thrust of this level to make a sustained flight. And at other lift equations or at other velocities of flight, I need a thrust much higher. That's the requirement of propulsion. So aerodynamics guy will say, boss, my job is done. I have given you extremely efficient CL by CD. I have given you a range at which it will play. But unless you give me an engine which will satisfy it, my aircraft will not fly. That's the need of propulsion. Now, let us look at a different angle, which means angle of attack. And where is it coming? It is coming in the maneuvers that we have to do. You remember this equation, right? At increased velocity, the thrust profile goes up and down like this. At one point where you have a very high angle of attack and very low velocity to sustain that lift, which means these high angle of attack operations, thrust requirement is actually higher than the optimum low. At a very low angle of attack, which is this almost zero angle of attack, point A, larger V infinity and hence larger dynamic pressure causes small CL lift coefficient, and hence drag is high. This is what we just looked at. Drag. So we know that this punishing guy will ensure that at higher velocities, which are these V's, the total thrust required will go up exponentially. And that is the beauty of this curve. At high angle of attack and low angle of attack, what are the thrust requirements? This has important implication in designing of a fighter jet, which has to transition between these very rapidly and very often, which means the requirement on the thrust changes with time drastically, and therefore all the components need to be designed such a way that they ensure the delivery of the consistent thrust as required with as time profile as needs to be adjusted by the flyer or by the specifically the pilot, or fighter pilot in simple sense. Now, once looking at this, we also now know that lift induced thrust which computes. So what we are doing in this graph is simply resolving thrust component into two parts. One, we say thrust because of drag, which is because simply the function of drag profile and induced drag profile, and thrust because of the lift. What does that mean? As you keep increasing velocity, the drag will ensure thrust goes up. But as you keep increasing velocity, the lift, the front, will keep it bringing it down. And hence, when the drag wins, the thrust requirement wins. That's the simple explanation. Now look at the power plants of how this drag induced and lift induced thrusts are delivered. You have mainly two types of engine common in aviation. One is reciprocating piston with propeller, which means it works on a principle that the reciprocating piston derives the propeller. So in a simplistic way, what happens is you have this propeller here which rotates, and the rotation is governed from here using the reciprocating piston arrangement. This engine is majority of the times used primarily to ensure that power is delivered and not the thrust is delivered. Whereas the jet engine, which has either a turbofan or a turbojet, takes out a large portion of air through its duct, which has a fan or a compressor aligned with it. If it is a simple turbojet, there is not even a fan. The direct air is induced and compressor does a work. We will see this detail in the next part of lecture series in chapter 2 and 3. But simplistically, the turbo has a closed-ended engine like this, whereas a propeller or a piston has open portions of these moving parts. The whole idea is the requirement of the thrust or a power. The reciprocating piston with propellers are rated in power, whereas these are rated in thrust. The power applications are more suitable when you have smaller velocity, smaller thrust requirement operations, whereas the jet and the turbofans are more suitable for handling higher velocities, simply because at extremely high velocities up to Mach 0.8, 0.9, these engines are not proven to be extremely rugged, and the failure modes in structures coupling with aerodynamics go up substantially compared to this closed and simple intake based turbofan or turbojet engines. All military engines will have simple turbojet or turbofan because of the extreme demand of variation of thrust, as we saw here with time, because of these maneuvers. Now, in the jet engines, which are either turbojets or turbofans for military applications, the thrust is a force in kg meter square or newtons. For example, PW 4112, classic engine in pounds is rated by the manufacturer as 98,000 pound of thrust, almost 50,000 kg or 50 tons approximately of the thrust. It is that powerful engine. Piston driven engines in power are always rated in watts or kilowatts, or in HP if it is a BS unit. Right? So that is the importance. Let us take one example. When aircraft is in level, which has no acceleration in the flight, which means simply the aircraft is moving in a straight line without any acceleration, the components, as we saw, are resolved, and so there is no requirement of the thrust. What do we need in terms of our thrust requirement? You simply see that power required is thrust into velocity, and so it is Newton into meter per second square. So it is a power rated engine that you will use, And if you use a power rated piston engine, you will have to specify what wattage is required by first computing the velocity and then computing the thrust required. It is as simple. Having understood this now, let's recap of what exactly are we thinking in terms of propulsion here. We understood that from history what the propulsion essence was to drive forward the engine. In propulsion, we also discussed in detail the requirement of the thrust that is imposed on an engine as its deliverable based on the maneuvers that aircraft has to perform. And therefore, we made ourselves very clear on how thrust goes up or down with what maneuvers that are required and how it is optimized by optimizing aerodynamic design. Having understood this aircraft, let's very briefly talk about space propulsion. In space propulsion, you have an object which needs to be taken from ground and put it in a high orbit, which means the entire work is required to be done so that it overcomes the gravitational energy that is stored at the ground. We know that at a higher and higher altitude, gravitational potential will be lower, so energy stored is lower. It is other way around if you think of in a classic example. So from the ground state to the state in the orbit, the entire work that needs to be transferred has to be derived from a power source, which is a rocket engine. So in a rocket engine, the idea is not that an object will fly from a fluid, but idea is that object will get lifted off and it will do a work against the gravitational potential field so that it gets up and is stored in the orbit. And in the orbit, you have to give it a velocity so that the centrifugal force ensures that it remains in that orbit. This entire energy transfer is derived from space propulsion system in a simple black box term. The space propulsion can be solid rockets, a liquid rocket, or a combination of two as a conventional PSLV or GSLV of ISRO is. But the whole crux is you burn a fuel, pass it the hot gases through nozzle, derive an energy from that fuel, and impart it in the form of high velocity and direction to an object which is lifted from the ground and placed in the orbit. That's where the requirement of space propulsion comes in. So aircraft and space, we discussed in detail what is the requirement of the propulsion. You may be wondering where in the GATE this question will come, and simply I will tell you one question which had come a few years back in one GATE example, where they had asked that if you have engines of the aircraft fail, can an aircraft still fly? This was a tricky question because what do you mean by fly has to be read in conjunction with the options given. And the options given were it cannot sustain a cruise mode, it has to come down and it will come down as a glider. That was the correct option was. This is because once the propulsion has stopped functioning, you cannot further supply energy to the flying object to sustain a flight. It only will come down as a glider as we discussed. You can only optimize its glide slope so that you get maximum breathing time. So if engines fail, it cannot sustain its motion. And that's the crux of aircraft propulsion.